Speed balancing is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video, Speed Balancing, gives additional definitions, hints, and suggestions on how to quickly and correctly solve your balance equations for your systems. If you haven't yet seen how to keep your balance, go back and watch it so that you can more fully understand this video. PFD. Process flow diagram or flow sheet. A schematic drawing of the mixers, dividers, separators, reactors, and other unit operations used in the process. Recycle. Part of a product stream is returned to the feed of a process. The recycle loop in this PFD is highlighted in red. Bypass. Part of the feed is routed around a process and mixed with the product. The bypass in this PFD is highlighted in red. Purge. A stream used to prevent buildup of trace components in a recycle loop. It has been circled in this PFD. Tie component. A component of the feed which is unchanged by a process. Usually useful for calculations, but never necessary. Overall balance. Treating a PFD as a black box with only inputs and outputs as indicated by the red line. The overall balance has an input of the feed and outputs of the purge and product. Solving your system equations. Here are some quotes about solving engineering problems that apply to chemical and thermal processes. Engineering is solving story problems where you often have to make up the story. Bookkeeping is just arithmetic and definitions, but it needs to be done correctly. There are many ways to solve a problem correctly. You want to develop a systematic approach and not treat each problem as an isolated issue. Since the first balance equations we'll work on solving are material balances, here is one useful technique for solving them. Later on, we'll add additional balances to step 6. 1. Draw a flowchart, PFD, and fill in all given variable values. 2. Convert quantities to a consistent set of units. 3. Choose a basis of calculation, usually an amount or flow rate of one of the process streams. 4. Label unknown stream variables on the chart. Use a consistent system of labeling. 5. Because volumes and volumetric flow rates are not conserved quantities, convert stream volumes to masses or moles, and volumetric flow rates to mass or molar flow rates. 6. Convert mixed mass and mole units to either all mass or all mole units. 7. Write material balance equations. 8. Write other problem constraints as equations. Number 9. Do a degrees of freedom analysis. Count the number of unknowns and the number of independent equations. Are they equal? What did you forget? 10. Solve the equations. 11. Convert the answers to desired units. Here's an example of applying the steps. The problem states, a bathtub with a partially open drain valve begins filling with water at a rate of 5 gallons per minute. The partially open valve is modeled by an equation relating the outlet flow rate to the depth of the water. V dot out equals 205.7 times the square root of h, with the depth h in centimeters and the flow rate V dot out in liters per hour. What is the steady state depth of the water in inches? Note, the solution given below is for the steady state, where the flow in equals the flow out. Solving the transient problem for the time to reach steady state involves using a transient mass or volume balance with an accumulation term. It requires the cross-sectional area of the bathtub and results in a nonlinear ordinary differential equation that must be solved. Here's the solution, with the step text given in italics. 1. Here's a PFD with the input and output labeled, along with the variable and given information. 2. Since the units are mixed, not all SI or American engineering will convert to SI to work the problem. Gallons per minute and liters per hour to cubic meters per second, centimeters and inches to meters. The conversions are as indicated. 3. The most useful basis is the input flow rate of 5 gallons per hour, or 3.155 times 10 to the negative 4 cubic meters per second. There are other less useful choices. 4. We already labeled the streams in step 1. 5. There is no value in converting to a mass flow rate for this problem because we're going to assume the temperature of the water, and therefore the specific volume doesn't change appreciably. If we had to convert, we would use the approximate value of 1,000 kilograms per meter cubed, which is true at 4 degrees Celsius. 6. Not applicable for this problem. 7. The mass balance is that at steady state, the mass flow rate in equals the mass flow rate out, and therefore the volumetric flow rate in equals the volumetric flow rate out, because m dot equals rho v dot, and we assume rho doesn't change. 8. The problem constraint is v dot out equals 205.7 times the square root of h, which will convert to meters and cubic meters per second, as discussed in the most annoying equation conversion video. 9. We have two equations, the volume balance and the valve equation, and two unknowns, the volumetric flow rate out and the steady state depth. 10. The solution is v dot out equals 3.155 times 10 to the minus 4 meters cubed per second, and h equals 0.3049 meters. 11. The depth in meters converted to inches is 12 inches. For the curious, here are some notes on the solution. The given note number corresponds to the step solution number. 1. If there were more species than one, water, we would have labeled the PFD with the species, and if known, the flows or compositions. 2. See if furlongs per fortnight is a thing for details on conversions. 5. Neglecting the change in density with temperature will only affect the answer in the fourth significant digit, so it will not appreciably affect the answer. 8. The details of the conversion of the equation are on the web page for the video. 10. A more detailed solution is on the web page for the video. Here are some speed tips for solving problems quickly. 1. If it's not needed, don't solve for everything. Just solve for the minimum required for the answers. 2. Write equations in order of number of unknowns from fewest to most. 3. Try overall balances first. 4. Check out if any tie components would be useful. 5. Remember that mole fractions or mass fractions add up to 1. 6. Usually, solving a recycle loop requires a complete set of equations around the loop. The takeaways are 1. Learn to recognize things given in the definitions like a PFD, recycle, and bypass. 2. Develop a systematic style to set up and solve problems. Use the given style if you don't have your own. 3. Check out the speed tips to see if they help. Thanks for watching. This video is brought to you by the DOFPro team.